Hey guys, in this video I'm going to show you a simple way to estimate how long a 12-volt battery can run your TV. First, we'll take a look at how much electricity your TV uses and how you can easily figure that out. Then we'll go over how much energy you can actually get from a battery like this. These two numbers are really all you need to get a pretty accurate estimate of how many hours your TV can run on a single charge. I'll also be running my own TV on a 12-volt 100 amp hour battery and measuring its energy use so we can compare the math to real life results. So make sure to stick around till the end of the video. Let's get into it. To give you a quick idea of what to expect, here's a table that estimates how long a 12-volt 100 amp hour battery can run TVs of different sizes and types. For example, if you have an LED TV around 40 inches in size, you can expect it to run on a fully charged 12-volt 100 amp hour battery for about 20 to 25 hours before the battery is fully depleted. If you're using a plasma TV around the same size, you will likely only get 6 to 9 hours of runtime, or maybe even less, since these older TV technologies consume a lot more power. Keep in mind that these are rough estimates based on my own research. If you want a more accurate number, you will need to look at the actual power specifications of your TV. So let's talk about that. If you take a look at the back of your TV, you'll usually find a specification label with a few electrical ratings. For example, this is a 32-inch LED TV, and if we look at the label here, we'll see a power consumption rating of 45 watts. Now, that's the power rating of the TV. What we actually need to estimate runtime is energy usage, which is measured in watt hours, but we can easily calculate that from the power rating. For example, if this TV runs for 1 hour, it will use up to 45 watt hours of energy. Notice I said up to 45 watt hours, not exactly 45. That's because the 45 watt rating represents the maximum power the TV might draw. As I explained in a previous video, the actual power usage will vary depending on things like screen brightness and volume. So when you use the wattage rating from the label, the energy number you calculate will likely be an overestimate, which means your runtime estimate will probably be an underestimate, and I'll actually demonstrate that in a couple of minutes. Still, it's a great figure to use because in these situations it's better to underestimate and be pleasantly surprised than to overestimate and end up disappointed. Batteries have two main electrical ratings: voltage, measured in volts, and charge capacity, measured in amp hours. You can use these two numbers to calculate the energy capacity of the battery, measured in watt hours, using this formula. So, for example, if you have a battery rated at 12 volts and 100 amp hours, its total energy capacity would be 1200 watt hours. But keep in mind that depending on the type of battery you're using and how long you want it to last, you may not want to use all 100% of its capacity. See, the deeper you discharge a battery each time you use it, the more you decrease its overall lifespan and ability to store energy. In other words, the higher the depth of discharge, or DOD, the fewer charge-discharge cycles it takes before the battery loses a significant portion of its storage capacity. But this effect isn't the same for all batteries. It depends on the type or chemistry of the battery you're using. Most batteries people use for these applications will fall into one of the two common types: lead acid or lithium. For lead acid batteries, the recommended depth of discharge is 50%. At that level, it typically takes around 500 to 1000 cycles before the battery loses something like 40% of its storage capacity. Lithium batteries, on the other hand, can handle a 100% depth of discharge and still last for thousands of cycles before any significant reduction in capacity. So, if you're going to be using the battery on a regular basis and want to optimize its lifespan, what really matters isn't the rated capacity but the usable capacity. If you're using a 12-volt 100 amp hour lithium battery, you can use the full 1200 watt hours of energy that it can store. But if you're using a 12-volt 100 amp hour lead acid battery, you might only want to use 600 watt hours before recharging it. That being said, if you're only using the battery occasionally, like for camping trips or during power outages, I wouldn't worry too much about all of this. Now, in a perfect scenario, we could just divide the battery's capacity by the TV's hourly energy usage that we've calculated and call it a day. But in reality, to run a TV off a battery, we need an inverter, which will convert the 12-volt DC power from the battery into the 120-volt AC power that your TV needs. That conversion is not 100% efficient. Even high-end inverters typically operate at 93 to 97% efficiency, and chances are you're not using that kind of inverter for a small setup like this. Also, an inverter's efficiency depends on how much of its rated capacity you're actually using. The less you load it, the more inefficient it becomes. So, depending on the wattage of your TV, if you're using a 200 watt or 300 watt inverter, you're probably getting around 85% efficiency. If you're using a 5 or 700 watt inverter, it would be safer to assume something more like 75% efficiency. With everything we've discussed so far, here's this simple formula you can use to calculate your TV's runtime. So for example, let's assume the inverter is running at 75% efficiency and I'm using a 12 volt 100 amp hour lithium battery. That gives me access to the full 1200 watt hours of usable capacity. In that case, the TV would run for about 20 hours. Now, if I was using a lead acid battery and I didn't want to discharge it below 50%, I would only have access to 600 watt hours of usable capacity. With that setup, my TV would only get 10 hours of runtime. So to find out how much power my TV actually uses and how much energy it would consume over 1 hour, I set up the system and I plugged the TV into the inverter through an electricity monitor. I then left the TV running with its usual settings around 50% volume and 100% brightness. At around the 1 hour mark, I checked the electricity meter and as you can see, the TV had used 35 watt hours of energy. Now in this setup, I'm using a lead acid battery and a 500 watt inverter. So let's say I don't want the battery to drop below 50% and I'll assume an inverter efficiency of 75%. Using our previous formula, I get an estimate that the TV could run for about 12 hours and 15 minutes. That's almost 3 hours longer than the estimate I got using just the TV's rated power consumption. In future videos, I'll be covering even more interesting topics around batteries, solar panels, and all things related to off-grid and DIY power. So if that's something you're interested in, make sure to subscribe to the channel so you don't miss out. That's it for now. If you found this video helpful, don't forget to give it a thumbs up. This will allow more people to find it. Thanks for watching and I'll see you in the next one.